Here in this video, we are solving two videos from the chapter Nuclei of class 12. Both appeared in the NEET examination 2020 and 2021. We'll start with this first question. The half-life of radioactive material is 100 hours. The fraction of the original activity that will remain after 150 hours will be how much, right? So he is asking how much of the radioactivity will be still there, or else how many nucleons will be still present after 150 hours if its half-life is 100 hours. There is a relation that we know that n by n0 equal to 1 by 2 whole power of small n. You shall know what these terms are. N is number of nucleons present after certain time that was given in the question, like 150 hours. N0 is initial number of nucleons. N is can be expressed as small t by capital T. T is the time after which we are trying to study. Capital T is its half-life period. Knowing the terms, we want to calculate the fraction of original activity, means number of nucleons present to the initial number of nucleons. 1 by 2 power of n. In the place of n, as I told you, I have to write time after which you want to calculate by half-life period. So 1 by 2, we want to know after 150 hours whose half-life is 100 hours. That is 1 by 2 power of 3 by 2. Then what we can say is the answer is number of the nucleons present. N by n0 is 1 by 2 power of 3 by 2. I can write the 2 power of 3 by 2 as 2 power of 1 by 2 plus 1. That because 1 by 2 plus 1 is 3 by 2. That is 2 power of 1 by 2 into 2 power of 1. In the power, you can add the powers if the bases are same. 1 by 2 plus 1 become again back to 3 by 2. This is 1 by 2 root 2. So n by n0 is 1 by 2 root 2 is the solution for that given simple problem. Let's have a look at the next question given. What is given there is the half-life of a radioactive sample undergoes alpha decay is given for a half-life is given. The number of the nucleons in the sample is, if the number of nucleons in the sample is something, then the activity of the sample is nearly how much? So to solve this problem, we shall know the basic law called law of radioactivity. As per law of radioactivity, the number of the nucleon disintegrated per the second called rate of disintegration is directly proportional to number of the nucleons present in the nucleus. Proportionality can be eliminated with a constant called decay constant. Of course, there will be a negative sign because this is disintegration, but here we are interested only on the magnitude. Magnitude of integration is lambda into n, where lambda is a constant called decay constant. Actually, from this relation, it is simplified further. You will get into this relation. I am not deriving that relation in this video. I have already done it in the chapter Nuclei. You can find it in the playlist of Nuclei. But we know the relation between half-life period and decay constant as lambda equal to 0.693 by half-life period. This derivation also I have made. Please look into that playlist. So I can write dn by dt is 0.693 by half-life period and the number of the nucleons present. So if I substitute the data, I will simply get the answer because you want the rate of disintegration. Activity of the sample means rate of disintegration. dn by dt equal to 0.693 by half-life period is given for you. 1.4 into 10 power 17 into n is the number of the nucleons present, that is 20 into 10 power 21. So if I further simplify this, 1.4 20 into 10 power 21, 10 power minus 17, that will become 10 power plus 4 automatically. Then what we can this is 2.0, it's not 20, so I have to write 2.0, it's not 20, it was given in the problem as 2.0. So the answer is 0.693 into 2 or 2.0 by 1.4 into 10 power 4. So this is 0.7, that will become 693 by 7 into 10 power 4. So if I calculate that value, it will come close to 0.99 into 10 power 4, that is close to 10 power 4. It is measured with a unit called becquerel in the name of a scientist, Henry Becquerel. So the answer is 10 power 4 becquerel. That's how we solve this problem. Thank you for watching.